Okay, good morning again. This is Professor David J. De Los Reyes. Okay, my next topic will be a long video format. This is a new video format topic of mine. This is DC circuit. So actually, our topic for this morning will be a continuation of my DC circuit long video format topic. DC circuit lesson number 5. Okay, let's proceed. My topic for this morning, a long video format, an addition to my long video format videos. Okay, it's a complete lesson, guys. The title of the topic will be DC Circuit, lesson number 5. Okay, I am marking my lessons by numbers. So if you try to watch my videos, they are in sequence from number 1 till finish. Okay. The title of the topic for this morning will be Parallel Connection Concepts. We are now through with the series connection concepts. Okay? I have discussed already what's the marking of a, what you call this, series connection. I've given you the formulas needed. How come the connection is a series connection? How come it is to be a series connection? Okay, I give you formulas, I give you the derivation, I give you example problems. So actually, under the series connection concepts, I think we have already finished the series connection concepts. So for this morning, I will be discussing the parallel connection concepts. We are just discussing it gradually. Okay, we are through with the series connection. We are now on the parallel connection. So actually, the more interesting part is actually the series parallel connection because it is more complicated than the series in parallel. But our knowledge on the series and parallel connection, we will be using it under series parallel connection. That's why I could not discuss series parallel connection immediately without knowing series and parallel connection concepts. Okay, let's proceed. The figure for a parallel connection, it will be this. Okay? This is the current circuit, so supposed to be the power supply is a battery. What could be a battery or a direct current generator maybe. And we are given three resistances in parallel. Okay? This is R1, this is R2, this is R3. For the meantime, the number of N is just equal to 3. Where N represents the number of resistances in parallel. Because the formulas I gave you, this is just true for N is equal to 3. If the number of resistances that are connected is actually 4, they should be 4, right? It should be I1, I2, I3, I4. Even the resistance, there should be 1 over R1, 1 over R2, 1 over R3. Okay, I will try to discuss first the figure. So the connection is parallel. How could we say that the connection is parallel? If in the series connection, for it to be series, the current passing through all the resistances will be equal, right? That's for a series connection. But for a parallel connection, that will be a different story. Okay, the parameter that is common to all the resistances will be different. It is not current. The common parameter to each individual resistance is actually the voltage E. This is E. Because the voltage across R1 is actually designated as B1. The voltage across R2 is designated as B sub 2. And the voltage across R sub 3 is designated by B sub 3. Okay? And for a connection to be a parallel connection, this should be the formula. Okay? The voltage across the source is the same as the voltage across R1, same as the voltage across R2, same as the voltage across R3. So for a connection to be parallel, the applied voltage should be equal to V sub 1, equal to V sub 2, equal to V sub 3. Okay? That's the difference of the parallel connection, okay, compared to the series connection. Because for the series connection, the common there is actually the current, that is I total is equal to I sub 1 plus I sub 2 plus, no, this should be equal. Sorry for that one. Equal to I sub 3. This is for series. Okay, so you now know the difference. For a series connection, the current is common. For a parallel connection, the voltage is common. Right? It's all the same. The applied voltage is same as V1, same as V2, same as V3. Okay? Assuming the connecting wires got negligible resistance. Because if there is a resistance here which is not equal to 0, that's a different story. So for the meantime, for the connection to be parallel, we assume that the connecting wires got 0 resistance. So on the figure, I didn't place any internal resistance here. But if there is, that's a different story. Okay? So the formulas needed for parallel connection, it is this one. The applied voltage is same as the voltage across R1, same as across R2, same as across R sub 3. Okay, let's try to bring out the formula needed for the current. For a parallel connection, the total current is equal to the, what they call this, algebraic sum. Algebraic, it's not vectorial sum because we are on this circuit. All the one we are adding all real numbers, so it will just be simply algebraic sum. So I total will be equal to the sum of I sub 1 plus I sub 2 plus I sub 3. So I place it here. If the number of resistances which are connected in parallel is just 3, I total will be equal to I sub 1 plus I sub 2 plus I sub 3. This is very important. Because in the computation of the so-called total resistance for a parallel connection, we will be needing this formula here. Okay? It will start from here. That's why I place it here. The third formula for parallel connection, 1 over R total, okay, it's a fraction, should be equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is the formula on how to compute for the total resistance if the connection is parallel connection. Okay? Okay, let's try to bring out the derivation of the total resistance. Okay? Derivation. In general, the voltage is actually the product IR, right? So if we try to compute for current, it will be voltage over R. Okay, and we will equate this B here to BE for a parallel connection, the applied voltage. So by using this equation here, okay, this will come out with the proper subscript, right? That is meaning the total current will be the total applied voltage over R total. The current passing through R1 should be the applied voltage over R1. The current passing through R sub 2 should be the applied voltage divided by R2. And the current passing through R sub 3 will be the applied voltage over R sub 3. It emanates from here, right? So I just applied this equation to each individual branch of the circuit. Okay? Then going back to this equation here, if the number of resistances which are connected in parallel is 3, this should be with subscript 3, the last one, right? Okay? So I total will be equal to the algebraic sum of I1 plus I2 plus I3. These currents are just real currents. It got no, what they call this, imaginary part. For a DC circuit, they are all real, right? So substituting these four equations here to this equation, what will come out? So I place it there, substituting. I total will be E over R total. I1 will be equal to E over R1. I sub 2 will be equal to E over R sub 2. And I sub 3 will be equal to E over R sub 3. Okay? Simplifying. I will bring out E. Okay? E times 1 over R total is actually E over R total, but I could make it like the product of E. Okay? The operation will be multiplication, right? The product of E times 1 over R total is E over R total, so meaning to say E over R total can be written as E over 1 over R total. And this should be equal to, again, on the right hand side, this is now algebra, right? If we try to observe the numerator, each individual numerator contains an E, and actually we could factor out, right? That's algebra. So again, this is we bring out or we brought out E. It's a common factor, right? So what will remain on the right hand side on this portion here will be 1 over R1, 1 over R2 plus 1 over RT closed quantity. The product of all of these times E is just this. Okay? And again, the usual error of students actually, this is where we can cancel now. The operation on the left hand side is multiplication, and the operation on the right hand side is also multiplication with regards to the quantity. So actually this E here cancel with this. Okay? Actually, there is a plus sign here, but this is 1 under quantity. So meaning to say the product of E times this quantity, the operation is multiplication. So we are free to cancel. Okay? That's the number one requirement. Even the cancellation on the numerator and denominator, the operation on the numerator and denominator should be multiplication, so we could cancel. Okay? That's why I've discussed this one in the common error for students. So this E here cancel with this because the operation on the left is multiplication, the operation on the right is multiplication. So this E here cancel with this. What will come out? 1 over R total equal to 1 over R1 plus 1 over R2 plus 1 over R3, okay, ohms. The unit is ohms. If the value of N is equal to 3, and what is N? The total number of resistances which are connected in parallel. So if N is equal to 4, this should be plus 1 over R sub 4. Okay? If N is equal to 5, we add plus 1 over R sub 5. Okay? Just be very flexible. So meaning to say, if the last one here is R sub 3, the value of N is just 3. Okay? We don't have to, what you call this, disagree with that. Okay? There is a special case under parallel connection because sometimes if we try to expedite our solution, okay, there is a special formula. If the total number of resistances is just only 2, which are connected in parallel. So the special case, if only 2, okay, resistances are actually in parallel. If there is only 2, right? This will be R1, this will be R2, this will be, sorry for that one, that will be R total. Okay? So if there are only two resistances which are connected in parallel, am I still on camera? Okay. To get the total resistance, okay, we will be using this formula. You don't have to pass by this one anymore. You just use this one. Okay. And to arrive at this one, actually it also emanates from here. That is, if there are only two R's in parallel, by following this, 1 over R total should be equal to 1 over R1 plus 1 over R2 if there are only two resistances in parallel. Only two, R1 and R2. So, 1 over R total should be equal to, if we try to simplify the right hand side, again, this is algebra. We are adding two fractions of different denominator. So we cross multiply this, right? So 1 times R2 will be R2, R1 times 1 will be R1, and the resulting denominator will be the product, R1 over R2. This is algebra, okay? Okay, that's algebra. That's why I'm telling you, if you don't know algebra, when you go to higher mathematics, you cannot proceed if you do not know algebra. Okay, I am just telling you this one because it's a part of the solution. The solution is easy, but the simplification is there are some algebra portions. So supposed to be we should do algebra, right? So the simplification of 1 over R1 plus 1 over R2 is just the sum of R2 R1, the product of R1 plus R2. This has been coming out from the short videos. They are calling it the so-called butterfly method. So actually, what is coming out on the short videos is actually very important. But don't saturate yourself with the butterfly method. Because when you go to the so-called actual problem, you will be needing those ones. But guys, okay, don't saturate yourself with the butterfly method. Okay, so 1 over R total will be the sum of R2, R1, all over the product R1, R2. And if we try to compute for this, okay, cross multiply this, right? Okay. 1 times R1, R2 will be R1, R2, and R total times the quantity R2 plus R1. If we try to compute for R total, it will be the product of 1 times this over the sum of R1 plus R2. This is the formula on how to compute for the single equivalent resistance if there are only two resistances in parallel. It will be the product of the first resistance times the second resistance all over the sum of R1 plus R2. This is in ohms. Okay? That's it, guys. I think these are just some of the concepts needed, formulas needed under the parallel operation concepts. Okay, so for those of you who would like to subscribe or watch my channel, okay, my channel is at youtube.com/@ProfDavidJ.Reyes. If you want to share it, please click share. I am assuring you, you will learn something from it. Okay, good morning from Los Angeles, Professor David J.